Welcome, curious minds, to another deep dive.
Great to be here.
Today, we're really digging into a cornerstone of organic chemistry.
Absolutely. We're building right on our substitution talks.
Our mission today? To unpack an entire chapter on elimination reactions from organic chemistry as a second language.
Yeah, pulling out all the key stuff, mechanisms, problem solving, the works.
We want to give you that clear shortcut to really understanding it.
Exactly.
Now, you might remember from last time, compounds with a leaving group can do substitution, right? One group swaps out.
That's the one. But here's the fascinating part. Those same compounds with the same leaving group,
Yeah.
they can also do something completely different. Elimination.
Okay, so they compete. Substitution versus elimination.
They absolutely do. Often you get a mix of products from both pathways happening at once.
Right, so predicting that outcome is crucial.
That's our goal for you today, giving you the tools to predict what's going to happen.
Okay, let's break it down. Substitution was replacement. What's the core idea then behind elimination?
Well, instead of replacing the leaving group, you actually remove a beta-proton at the same time as the leaving group pops off.
A beta-proton.
Okay.
And the result?
The result is you form a double bond in the molecule, pi bond formation.
Makes sense. And you mentioned parallelized with substitution, SN1, SN2.
Exactly. For elimination, we have two main mechanisms to explore, E1 and E2.
All right, where should we start?
Let's dive into E2 first. It's quite distinct.
E2 it is. So, molecular level.
Yeah.
What's happening? What's this dance look like?
The E2 process is really neat. It's a single concerted step.
Concerted meaning all at once.
All at once. A base comes in, grabs that beta-proton,
Okay.
and in that exact same moment, the electrons shift, form the double bond, and kick out the leaving group. Boom, one step.
Wow, no waiting around, no intermediates formed.
None at all. Straight from reactants to the alkene product. It's very efficient.
That seems important. Does that affect reaction speed or requirements?
It definitely can. And that single step tells us something else related to the name, E2.
Right, the two. What's that stand for?
Because both the starting molecule, the substrate, and the base are involved in that one crucial rate-determining step.
Both molecules colliding at the same time.
Precisely. It's considered a bimolecular process. Hence, E2.
Bimolecular. Got it. Okay, thinking back to SN2. Tertiary substrates were a problem, right? Steric hindrance.
They were indeed.
Yeah.
Too crowded for the nucleophile to attack.
So is E2 the same? Does it struggle with bulky tertiary substrates?
That's a really important question, and here's a critical difference.
Okay.
Unlike SN2, tertiary substrates often undergo E2 reactions quite rapidly, sometimes even faster than primary or secondary.
Faster? How can that be if it's still crowded?
Because the role of the reagent is different. In E2, it's acting as a base. It just needs to pluck off a proton from the outside edge of the molecule.
It doesn't need to get deep into the center like an SN2 nucleophile.
Exactly. Removing a proton is generally much less sterically demanding, so tertiary substrates, often great for E2.
That's a key distinction to remember. Okay, so E2 forms a double bond. But what if there's more than one place it could form?
Good point. That brings us to regiochemistry.
Regiochemistry, where the reaction happens, right? Like Markovnikov addition.
Precisely. Same concept, different context. If you have different types of beta-protons.
Meaning protons on different carbons next to the leaving group?
Yes. Removing one type might give you one alkene. Removing another type gives a different alkene.
And these different alkene products, are they equal?
Not usually. We classify them by how many non-hydrogen groups are attached to the double bond carbons. Monosubstituted, desubstituted, tri, tetra.
And generally, more substituted means more stable.
Generally, yes. More stable.
And these products have names, I bet, like Zaitsev.
You got it. The Zaitsev product is the more substituted alkene. It's usually the major product because it's more stable thermodynamically.
Usually, but not always. Here comes the organic chemistry twist.
You know it. There's the Hofmann product, too, which is the less substituted alkene.
Okay, so Zaitsev is usually major, Hofmann minor. When does that flip?
This is where it gets really cool and useful. You can actually control the outcome.
Control it.
By choosing your base carefully. If you use a really big sterically hindered base.
Like what's an example?
Potassium tert-butoxide is the classic one, often written as t-BuOK or LDA, lithium disopropylamide. These things are huge.
Okay, so a big, bulky base.
That bulky base has a really hard time reaching the protons that would lead to the more substituted Zaitsev product, because those protons are usually more crowded.
So it takes the path of least resistance.
Exactly. It preferentially grabs a less hindered proton, typically one on a methyl group, or a less substituted carbon,
leading to the less substituted alkene.
leading to the Hofmann product becoming the major product.
Wow. So choice of base dictates regiochemistry in E2. That's a powerful tool for synthesis.
It really is a fundamental practical tip.
Okay, so that's where the double bond forms. What about the geometry around it? Cis versus strands.
Right, that's stereochemistry. E2 reactions can be stereoselective,
Meaning?
meaning if both cis and trans isomers can form, you'll usually get more of one than the other.
And which one is usually favored?
Typically, the trans product is favored. It's generally more stable because the larger groups are further apart, less steric clash.
So stereoselective favors trans. Is it ever more specific than that? Can it only form one?
Yes. This is another key E2 feature. It can be stereospecific.
Stereospecific. Okay, when does that happen?
This happens when the beta carbon, the one losing the proton, has only one proton attached to it.
Only one beta proton available.
In that situation, a very strict geometric requirement kicks in.
Ah, this sounds important.
It is. The proton being removed and the leaving group must be antiperiplanar to each other during that concerted step.
Antiperiplanar. Okay, fancy word. Break that down for us. What does it mean visually?
It means they have to be positioned on opposite sides of the carbon bond that's becoming the double bond, 180 degrees apart. Think staggered conformation.
Opposite sides, 180 degrees. Like looking down a Newman projection.
Exactly. Newman projections are the perfect way to visualize this.
So if you draw the Newman projection,
You rotate the molecule until that beta proton and the leaving group are anti-180 degrees apart. Then you see exactly where the other groups end up in the resulting alkene.
and only the product formed from that specific alignment can form.
Correct. If that alignment isn't possible, or if there's only one proton, only one specific stereoisomer, cis or trans, can be produced. It's not a preference, it's a requirement.
So if your Newman projections are rusty,
Definitely brush up. They're crucial for predicting stereospecific E2 outcomes.
good tip. Okay, that's E2. Concerted bimolecular Zaitsev Hofmann control antiperiplanar requirement. Quite a lot there.
It is, but it all connects logically.
Now what about the other one, E1? What's the 1 mean here?
The 1 in E1 stands for unimolecular.
Unimolecular. So the rate only depends on one molecule.
Exactly. The rate determining step involves only the substrate, not the base.
And unlike E2 single step, E1 is different.
Right. E1 is a two-step process.
Okay, walk us through those two steps.
Sure. Step 1 is the slow part. The loss of the leaving group all by itself.
Just pops off.
Just leaves. This generates a carbocation intermediate. This first step is slow and rate determining. Notice the base isn't involved yet.
A carbocation. Okay, alarm bells are ringing. SN1.
Exactly. That connection is vital.
So step 1 is leaving group leaves, forms carbocation. What's step 2?
Step 2 is fast. A base comes along, finds a beta proton on a carbon adjacent to the carbocation, plucks it off, and the electrons collapse to form the double bond.
Base removes proton from the carbocation intermediate.
Got it. So that first step, forming the carbocation, it's identical to SN1's first step.
Absolutely identical.
Yeah.
Slow formation of a carbocation.
Which means E1 and SN1 probably happen together a lot.
They almost always compete because they share that common first step and intermediate. If conditions allow for E1, they usually allow for SN1 too.
No.
Often get a mix.
Okay. And carbocation stability, that was huge for SN1 rate. Same for E1. Critically important. The rate of E1 is super sensitive to carbocation stability.
And so tertiary substrates react fastest, then secondary.
Precisely. Tertiary halides react much more readily than secondary halides via E1.
And primary.
Primary halides generally don't do E1 at all. Primary carbocations are just too unstable to form readily.
Same trend as SN1, same reason. Makes sense. What about bad leaving groups, like alcohols? Oh, wait.
Same fix as SN1. A poor leaving group like hydroxyl needs help. You typically protonate it first with a strong acid.
Like sulfuric acid?
Yep. That turns NHOH into NHOH2 plus fears off, which is basically water, an excellent leaving group. So treating alcohol with strong acid and heat is a classic way to drive an E1 reaction.
Acid catalysis, okay. So E1 also forms a double bond. Does it follow Zaitsev's rule favoring the more substituted alkene?
Yes, E1 processes also show a strong regiochemical preference for the Zaitsev product. The more substituted, more stable alkene is usually the major product.
Now with E2, we could use a bulky base to force the Hofmann product. Can we do that with E1?
Another critical difference here.
Let's hear it.
The regiochemical outcome of an E1 process cannot be controlled by the choice of base,
Cannot. Why not?
because the base isn't involved until after the carbocation is already formed. That carbocation intermediate is what dictates the product, and it will rearrange or deprotonate to give the most stable Zaitsev alkene, regardless of how bulky the base is that comes in later.
So E1 always aims for Zaitsev no matter the base. Got it. What about stereochemistry? Cis versus trans?
E1 reactions are not stereospecific.
Yeah.
There's no antiperiplanar requirement because the intermediate is a flat sp2 hybridized carbocation. Rotation is easy.
So no strict geometric rule like E2 sometimes has.
Correct. However, they are stereoselective.
Meaning they still prefer the trans isomer?
Generally, yes. Just like E2, when both cis and trans products are possible, E1 will typically favor the formation of the more stable trans stereoisomer. Stability wins again.
Okay, this is fantastic. We've got E2, we've got E1, their mechanisms, regiochemistry, stereochemistry, but now the big one.
The competition.
Exactly. Substitution versus elimination. SN1, SN2, E1, E2. How do we predict what actually happens in a real reaction? What products we get and which are major?
This is the ultimate challenge, you're right. It's where you synthesize everything.
Yeah.
And sometimes, yeah, one reaction clearly dominates. But often, you get a mixture.
So the goal isn't always just one product, but predicting all likely products and which ones dominate.
That's the skill, predicting the major and minor products. And we use a systematic three-step approach.
Okay, lay it on us. Step 1.
Step 1, determine the function of the reagent. Is it acting primarily as a nucleophile or primarily as a base? Or maybe both?
Why is that the absolute first step?
Because it fundamentally directs which pathway we consider. Substitution happens when the reagent acts as a nucleophile.
Attacking the carbon.
Right. Elimination happens when it acts as a base.
Grabbing a proton.
Exactly.
Yeah.
And here's the tricky part. Basicity and nucleophilicity don't always track together. Something can be a strong base, but a poor nucleophile, or vice versa.
Ah, that sounds like a major point of confusion. Can you give an example?
Sure. Let's compare atoms in the same row of the periodic table, like nitrogen and oxygen. H2N, a amide ion, is both a stronger base and a stronger nucleophile than HO, hydroxide. There, they parallel.
Okay, same row, they track. What about same column?
That's where they often don't parallel. Think about HO versus HS hydrosulfide.
Oxygen versus sulfur.
HO is the stronger base than HS, no question.
Right, oxygen is more electronegative, holds charge better in some ways. Wait, no, hydroxide is a stronger base. Okay.
But HS is actually a better nucleophile than HO.
What? How can the weaker base be the better nucleophile? That feels backwards.
It does seem counterintuitive, but it raises this important question about what these terms mean. Basicity is thermodynamic, how stable is the species? Nucleophilicity is kinetic, how fast does it attack?
Okay, kinetics versus thermodynamics.
Larger atoms, further down a column like sulfur or iodine, are more polarizable.
Polarizable, meaning their electron cloud is bigger, squishier.
Exactly. That electron density can distort and reach out more effectively as it approaches the positive charge of an electrophile. This creates stronger instantaneous attractions and leads to a much faster attack.
So big squishy atoms attack faster, even if they aren't the strongest bases.
That's the key idea. So things like HS, RS thiolates, and the alides iodide, bromide, chloride, they are generally much better nucleophiles than they are bases.
And the practical consequence.
They function almost exclusively as nucleophiles. When you see I, Br, Cl, HSRS, think substitution, SN1, SN2. Elimination is usually a very minor pathway, if it happens at all. They're too weakly basic.
That's huge. That simplifies things a lot for those reagents.
Okay, so how do we categorize all the reagents for prediction?
We can put them into 4 helpful bins.
Bin number 1.
Nucleophiles, only way. These are your strong nucleophiles, but weak bases. We just talked about them. Halides, Cl, Bri, sulfur nucleophiles, HSRSF. Focus only on substitution with these. Quick note. Sulfuric acid has sulfur, but no lone pair to attack. It's just an acid, not a nucleophile. Got it. Nucleophiles only. Bin 2.
Base only. These are strong bases, but poor nucleophiles. Think hydride ion, H from NaH, or those big bulky bases like tert-butoxide, t-BuOK.
Why are they bad nucleophiles?
Hydrate is small, not polarizable. Tert-butoxide is just too sterically hindered to attack a carbon effectively. So these guys strongly favor elimination, specifically E2.
Makes sense. Bin 3.
Strong nucleophile, strong base. These are the versatile ones that can do both well. Hydroxide, HO, and alkoxides like methoxide, CH3O, ethoxide, CH3, CH2O fit here. They're involved in bimolecular processes. SN2 and E2 competition is common.
Okay, the competitors. And the last bin.
Weak nucleophile, weak base. Think neutral molecules like water, H2O, and alcohols, ROH. They aren't strong enough to force SN2 or E2.
So they favor the unimolecular paths.
Exactly. They typically lead to SN1 and E1 reactions, especially with substrates that can form stable carbocations. They wait for the leaving group to leave first.
Brilliant categorization. Okay, that's step 1, analyze the reagent. What's step 2?
Step 2. Analyze the substrate and determine the expected mechanisms. Is the substrate primary, secondary, or tertiary?
Right, because we saw that matters hugely for SN1, SN2, and E1, E2 rates.
Absolutely. And now you combine the reagent category, step 1, with the substrate type, step 2, using a kind of mental flowchart. It's not about pure memorization, but understanding the interplay.
Understanding why a certain combo favors SN2 over E2 or E1 over SN1.
Precisely. Can we run through some highlights of that flowchart?
Please do.
Okay. If your reagent is nucleophile only, halides, sulfur.
Substitution land.
Right. Primary and secondary substrates will likely do SM2, tertiary will do SN1. Elimination isn't really on the table.
Simple enough. What about base only? Hydride, t-BuOK.
Think E2. Primary, secondary, tertiary E2 usually predominates because these are strong bases, and E2 isn't as bothered by sterics as SN2 is.
Okay. Now the competitive category. Strong nucleophile, strong base. HO-RO.
This is where it gets interesting. For primary substrates, SN2 usually wins out over E2. They're unhindered, easy to attack.
Usually.
Unless you specifically use a bulky base like t-BuOK. Then you force E2, Hofmann, even on a primary substrate.
Ah, using that steric control. What about secondary substrates with strong base?
For secondary, E2 typically predominates. Now, steric hindrance is starting to slow down SN2, making E2 the faster, easier path.
And tertiary with strong base.
Only E2 is observed. SN2 is completely blocked by steric hindrance. The reagent has to act as a base.
Okay. Clear progression there. Last category. Weak nucleophile, weak base. H2O, ROH.
Unimolecular reactions dominate here, SN1 and E1, especially with secondary and tertiary substrates that form stable carbocations.
And primer.
Primary substrates usually don't react much or react very slowly under these conditions. Their carbocations are too unstable.
And can we favor E1 over SN1?
Yes. High temperature specifically favors elimination, E1 over substitution, SN1, entropy-driven.
Fantastic overview. It really is about understanding the why, not just memorizing a table.
That's the only way to apply it effectively to new problems.
Okay, we've done step 1, reagent, step 2, substrate mechanism. What's the final step?
Step 3. Consider the specific regiochemical and stereochemical requirements for the mechanisms you predicted in step 2. Now you draw the actual products.
Applying all the Zaitsev, Hofmann, and stereochem rules we discussed earlier?
Exactly. Let's quickly recap those product details.
Go for it.
For SN2, nucleophile attacks the alpha carbon. Always get inversion of configuration at that carbon if it's a stereocenter.
Okay. SN1?
For SN1, nucleophile attacks the planar carbocation. Get racemization, a mix of both retention and inversion, forming both enantiomers if chiral.
E2.
For E2. Zaitsev product major, unless using a bulky base, then Hofmann major. It's stereoselective, trans-favored, and it's stereospecific, antiperiplanar required, if there's only one beta-proton.
Right. And E1.
For E1. Zaitsev product is always favored. Regiochemistry can't be controlled by base. It's stereoselective, trans-favored, but not stereospecific.
Perfect summary. Okay, let's solidify this. Example time. The book uses treating 3-bromopentane with sodium methoxide.
Great example. Let's walk through our 3 steps.
Step 1, reagent.
Sodium methoxide, NaOCH3, that's CH3O, strong base, strong nucleophile, our competitive category.
Okay. Step 2, substrate.
3-bromopentane. The bromine is on carbon 3, which is attached to carbons 2 and 4. That's secondary alkyl halide.
Secondary substrate, strong base.
Right.
What mechanisms compete?
Our flowchart says for secondary plus strong base, we expect both E2 and SN2.
And which one likely predominates?
E2 usually predominates over SN2 for secondary substrates due to increasing steric hindrance for the SN2 attack.
So E2 products equals major. SN2 products is minor.
That's our prediction. Now for step 3, predict the specific products. Let's start with the major pathway, E2.
E2 regiochemistry. Methoxide isn't bulky.
Right. Methoxide is small, so we expect the Zaitsev product. Removing a proton from C2 or C4 gives the same product. 2-pentene. That's more substituted than 1-pentene, the Hofmann product.
Okay, 2-pentene is the major regiosomer. Stereochemistry for E2.
E2 is stereoselective. 2-pentene can exist as cis and trans isomers. We expect the more stable trans 2-pentene to be favored over cis 2-pentene.
So major products are trans and cis 2-pentene with trans cis.
Exactly. Now for the minor pathway, SN2.
SN2 product, nucleophile methoxide, replaces the leaving group, bromide.
So we get 3-methoxypentane.
And SN2 stereochemistry. The starting material, 3-bromopentane, has a stereocenter at C3.
It does. And SN2 causes inversion of configuration. So if you started with R3-bromopentane, you'd get S3-methoxypentane as the minor product, and vice versa.
Wow. So for that one reaction, major products are trans-2-pentene and cis-2-pentene via E2 Zaitsev transfavored. Minor product is 3-methoxypentane via SN2 with inversion.
That's the complete picture. See how the steps build on each other?
Absolutely. It's a really powerful logical framework, takes the guesswork out of it.
That's the goal.
What a deep dive. Seriously, we've gone from the basics of E1 and E2 right through to predicting complex reaction mixtures.
Covered the mechanisms. The regiochemistry, Zaitsev versus Hofmann control is huge. The stereochemistry, antiperiplanar needs.
And crucially, that three-step strategy for figuring out substitution versus elimination.
And remember, it's not just memorizing rules. It's grasping the why. Why does structure matter? Why does base choice matter? Seeing those molecular forces.
That ability to synthesize the info, predict pathways, that really feels like mastering organic chemistry.
It absolutely is.
And that's what we hope for you, our listener, that you feel more confident, well-informed, ready to tackle these problems.
Which leads to maybe a final thought. Now that you understand this competition, this sensitivity to conditions,
Yeah.
can you think of other situations, maybe even outside of pure chemistry, where seemingly small changes in conditions or ingredients lead to dramatically different outcomes?
Ooh, that's a great question. Something to definitely mull over.
Keep those connections going.
We will. Thank you so much for joining our last-minute lecture family today for this exploration of elimination reactions.
Keep learning. Keep asking why.
And keep making those molecular connections. Until next time.